Okay, what do we have for this first one up here?
Forces holding together just molecules. Three molecules. They always hold them together. Yeah, they sometimes push each other.
Absolutely not.
Okay.
So the force, I mean, if you're talking about one being polar and one being nonpolar, then that's the absence of a force. So then, they control what?
Viscosity.
Sure. We'll go with boiling point and melting point. We haven't really talked about the viscosity yet, but viscosity and surface tension. They're not as strong as the chemical bonds that hold the molecule's atoms together, but they're at least as important to us because, melting point, boiling point, viscosity, surface tension, all those things have direct implications to how substances are used in our everyday lives. Methane, ethane, propane, and butane. Draw the structure of each and explain why the boiling point's different. So I've got a C with a bunch of H's around it. I got a C, two C's with a bunch of H's around it. I got three C's with a bunch of H's around it. And I got four C's with a bunch of H's around it.
Do you want us to draw them like this or in 3D shape? Is this fun?
This is fine. What do we have for boiling points for the methane? Looks like a negative, about negative 160, negative 90-ish, negative 40-ish, negative 1-ish. Okay. And these are all in degrees Celsius. So can you explain why the boiling points go up?
More to break apart.
What do you mean by more to break apart?
I guess there's more surface area around the outsides
Okay.
where the hydrogen's lying.
The easiest way to think about this, and this definitely is about surface area. The ability for them to be touching each other is, the analogy is Velcro. Shorter to longer pieces. So your butane is a longer piece of Velcro, so it's going to take more effort to separate it than it would be the short piece of methane Velcro. So the amount of energy needed to do that obviously increases. Okay. What do dispersion forces, dipole, induced dipole, dipole, and hydrogen bonding intermolecular forces have in common? Yeah, these are forces. These are the forces that hold covalent molecules together. Look up the melting points for neon and xenon. What's the difference between these two? So what was neons is, looks like it's about negative 250, and the xenon is about negative 110. So why is xenon have such a higher boiling point or melting point? Bigger. So what does that mean? Bigger. No, not more this isn't the Velcro analogy. Which analogy is this?
More mass.
What kind of intermolecular forces does xenon and neon have?
Dipole.
There's no dipole there. It's just atoms, right? And so there isn't a reason for the electrons to be on one side or the other. So then we're talking about dispersion forces, the weakest of those. So if I've got two neons and they approach each other, then what needs to happen is electrons need to be pushed to one side of the atom and the others need to have their electrons go towards, and so I get that temporary dipole. That, how many electrons do I have to deal with the neon? Less than xenon. If I look up there, there's 10, right? Each one of these guys have 10 electrons to disperse. And the xenon? Is it 54 electrons? Do you remember which analogy this one was now? Dodgeball. The 8.5 foot tall dodgeball versus the 8-inch dodgeball versus the 4-inch dodgeball. It's easier to flex that 8.5 foot tall dodgeball than it is to flex the 4-inch dodgeball. So don't want to get hit with a baseball. Don't really want to get hit with a softball, but would prefer to get hit with a softball even though they're not really that soft. Because what happens, what does a softball do a little bit better than a baseball does?
Deforms itself.
Deforms itself and not your face. Exactly. Yeah. If you've ever seen high-speed photography, video photography of a baseball or a softball being hit, the ball seriously squishes. It becomes half of its normal width if there's a full contact on a baseball. And the only way that happens is if the thing that it hits is not deforming at all. So difference relative to the other piece, I agree, it will deform some, but relative to the baseball, it doesn't deform, which is why Major League Baseball players are not allowed to use what? Okay, well that's another issue completely. That's about bat speed. Not that this issue isn't about bat speed either, but no. All the other levels of baseball get to use them, but not Major League Baseball. It's the difference between hearing a ball hit in Little League or in high school versus Major League Baseball getting hit. They're not allowed to use metal bats. The metal bat doesn't deform. So since it doesn't deform, that means more of the energy of the bat is transferred into the ball, and then the ball moves faster. So why is that a problem? Because that pitcher's only 66.6 away from the baseball, and he's actually closer than that because he's stretched out. So we're talking about 50-something feet. The amount of time that he has to react to that is well less than 1/10 of a second. So is he trying to catch the ball? Is he trying to dodge the ball? I mean, we've probably all seen a video highlight of a pitcher taking a ball, right? I remember in the 90s, a guy named Norm Charlton, who was a closer, took one to the forehead. Like it hit hard, and you know it was a problem because when it hit him, it went up in the air about 3 feet and then came back down. Why is that bad?
Because he wanted to have deformed on his head and bounced up.
It only bounced up 3 feet. Like if it had bounced up like 40 feet, that means the ball still had a whole bunch of energy, but instead it gave all of the energy to his forehead. He had a welt about almost the size of a baseball on his head formed in 10 seconds. It was pretty bad. And then blood trickling down the center of his nose. This is the same reason that sometimes golf clubs get banned by PGA Tour. They transfer too much energy to the ball, and so they don't want the sport to be dependent upon purchasing one style of club that somebody could charge a boatload of money for. That's why if you take this class at Oregon State, you only get to use a $5 calculator. You're not allowed to use a $100 calculator. They wanted it to be accessible to everybody. Requirements for something to exhibit hydrogen bonding. Let's go with the easiest part. A hydrogen atom must be present, right? So that hydrogen atom, what's the requirement?
Connected to a nitrogen or oxygen or fluorine.
Okay, and so boring, right? Why is this one boring? That's it. We're just talking about the HF molecule and other HF molecules if we're talking about intermolecular forces. But over here, the nitrogen and the oxygen can connect to more things, so I can have those on molecules, large molecules, or just larger molecules than just in HF. Why do the ingredients for vodka mix so well? What are the ingredients for vodka? Did you say methane? No, not that. I'm actually glad you know that, or don't know that. Ethanol, not ethane. Again, good. Oh, we can't see that. What? So those are the ingredients, but why is it that it can? Why do these mix so well?
Because they use nitrogen.
Yeah.
Yeah, I looked up the
No. 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 Do you see it on the internet?
What?
Okay, so we okay with there's hydrogen bonding and water, right? The ethanol molecule is an HCH HCHHOH. So there's hydrogen bonding, could be there or there, and it could be there. So this side over here has a partial positive on it, and this side here is a partial negative, partial positive, partial negative, partial positive. So the molecules have no problem mixing with each other, and there's full and complete mixing. You'll never like pull out a bottle of alcohol, some kind of alcoholic solution, and have those two guys separate out from each other. They will constantly be perfectly chaotically mixed. All right.